Okay, so today my intention is to finish our kind of lengthy diversion into linear algebra, and then we'll return to apply all those linear algebra concepts that we learned about to manifolds and tangent vectors and things of that nature. And then not today, but at some point next week, we'll go back and we'll talk about physical systems with rigid bodies and stuff like that. Okay, so last time, what did we do? We talked about, remember the setting. Okay, so the setting is the usual one, a finite dimensional vector space with a basis. Okay, so we talked about this collection of bilinear mappings is a basis for the set of all bilinear mappings. Okay. We talked about the matrix B for some bilinear mapping. Okay, and so I'll kind of rewrite this thing again. And so remember that B is a matrix which has components, which I'll now write like this. Okay, where these B sub JKs are the components, and they're simply obtained by evaluating B on the basis vectors. Okay, so these are the components of B in the basis. Okay, and then we had a long conversation about just what this matrix is, and more importantly, what it is not. Okay, so what it is it's the matrix of a bilinear map. That's just obviously by definition what it is. What it's not is the matrix of a linear map from V to V. But what we did decide is that associated uniquely to every B. So let me maybe, be a little bit explicit here. Okay, so if I have a B in here, this maps to this thing I call B flat, which was a linear mapping from V into B star. Okay, and we saw that the matrix of B in a basis for V is the same as the matrix for B flat in a basis for V and a basis for V, and then the corresponding dual basis for V star. Okay. All right. Okay, so that's kind of our starting point for today's lecture. So let's maybe, so So last time we looked at an example of a very simple vector space, namely, and we'll look at this example again. Okay, of v equals Rn and E1, En, the standard basis. Okay, so what we did last time was we saw what, so if we use the standard basis and represent a bilinear mapping by its matrix like this, what we did was we saw that the matrix representation of this basis is simply the matrix which has a 1 in the jth row and the kth column. Okay, so that's what we saw last time. Now what we're going to do is we're going to, kind of try to understand this business with an example. Okay, so let's let, and I'll give it a special name because it's a special thing. So let me, since it's the first time I'm using the symbol, let me actually try to write it so you'll understand what it is. That's a G. It's like the it's the G in the same font as that R. Okay. So let G Rn. Okay. So this is going to be the standard inner product for Rn. Okay, so what is the standard inner product? Well, the standard inner product takes vectors, u, and so u is, of course, going to be, as we always do, a linear combination of the standard basis vectors. And then v is going to be, there's no reason I shouldn't use j there. V is going to be a linear combination of the standard basis vectors. Sorry, let me just do the same thing here. All right, and what's the definition of the standard inner product for Rn? That thing which has the forbidden name of dot product that we don't talk about. Okay. Well, the definition of this thing, as you very well know, is just this. Okay, so you'll notice that I wrote a summation sign here. Why did I do that? Why didn't I write this as that?
Both the J's are superscripts.
That's right. So we'll see how to very soon how to repair that little notational inconsistency. But for what we're doing right now, you can't write it using the summation convention. Okay. All right. So what's the matrix for the standard inner product in the standard basis? Okay, I will take guesses. Okay, so remember what the definition is. The definition of the matrix is that in the ij or the jkth block of this matrix or component of this matrix, I put the inner product, in this case, of the jth basis vector with the kth basis vector. What will that be in this case? What's the standard inner product of the jth standard basis vector with the kth standard basis vector?
0,
unless,
j equals k.
exactly, okay? So, thank you. So it's, of course, the n by n identity matrix, which I write as that. Okay, so this is the identity matrix, all right, as opposed to the identity linear map. So we know that although this is the identity matrix, this does not mean that this thing, this thing, okay, independent of its matrix representation and a basis, this is not the identity linear map, right? It's not even a linear map on the same vector space. So if you have a linear map from a vector space to a different vector space, it certainly can't be equal to the identity, right? And so although this is the identity matrix, this is the identity matrix, this is not the identity linear map. Okay, it is, however, a linear map from Rn into Rn dual. Okay, so let me kind of write a few pieces of English attached to that. Okay. So the standard inner product, although it has the identity matrix as its matrix representation, is not the identity map. Okay, it's a bilinear map. It's incapable of being the identity map. But what is true? What is true? So I'm going to write it all out in big, long, full-blown English, just so that I do it. Okay, so we have this mapping, G, R, N, flat. And what is this a mapping from and to? So this is a linear mapping from Rn into Rn dual. Okay, so the matrix representative of this linear mapping, and so when I talk about the matrix representative, I need a basis for this and a basis for this. So the basis for this, I'm obviously going to use the standard basis, and the basis for this, I'm going to use the dual basis to the standard basis. Okay, so the matrix representation of G flat in the standard basis for Rn and the dual to the standard basis is the identity matrix. Okay, so that's what is true. Okay, and again, this sort of is in the category of so easy that it's possibly confusing. All right. Okay, now let's maybe patch up this little summation convention issue here. Any ideas on how we might do that? On how we might actually be able to use the summation convention to write an expression like that? So maybe let me sort of finish the example and sort of make some general comments. And then when I make the general comments, I'll apply them back to the example. If I have a general B on a general vector space, okay, then if I have a B and I apply it to a vector U And again, I'm gonna, as I always do, write U as the linear combination of the basis vectors, the basis vectors. And V similarly. Okay, then what's this? This is bilinearity. Okay, I'm going to split this sum outside B and similarly this sum. So I'm going to get U J V K B of E J E K. So now I'm using the summation convention. Okay, and by definition of the components, these are just the components of B. And it's sort of aesthetically more pleasing if you write it like this. Okay, so notice when you're using expressions with the summation convention, the order in which you write things is mathematically irrelevant, but sometimes things look better one way than in the other way. Okay, because these, after all, these are just multiplication of scalars, right? So it doesn't matter the order that you write. Okay, now if we go back to our example, okay, and so, the example we just talked about, then I know that what's Bij in this case? So the components of G, the standard inner product. Okay, so what are these? Well, we know what they are. They're the things which, when we put them in a matrix, make the matrix look like the identity matrix. And so that means that the components are 1 when J is equal to K and 0 otherwise. Well, we have a symbol for that. That's the Kronecker delta. But it's a different kind of a Kronecker delta than we were looking at before. Because the one we were looking at before had, superscripts and subscripts. This one just has subscripts. Makes no difference. It still has the same kind of a meaning. Okay. Okay, so then the standard inner product is that if you take the standard inner product and apply it to two vectors U and V, what you get. And now, so I'm just basically going to write this expression here, but now I'm going to introduce the summation convention in the same way that I have the summation convention here. Okay, but so it's just delta J K U J V K. Okay. All right, and so because if this was kind of a linear map from V to V, then we would expect this to have one superscript and one subscript. And the fact that they're both subscripts means that these delta JKs are not the components of the identity linear map, but are the components of a bilinear map. And it just happens that we've chosen a basis in which the components of the bilinear map assemble into the identity matrix. That's just sort of a coincidence. Okay. All right. Is that okay? All right. Now, let's look at a little bit in detail more about symmetry and definiteness. Of bilinear maps. Okay, so first of all, there's the obvious fact. Okay, so B, a bilinear mapping, is symmetric Okay, so remember that the symmetric bilinear mappings we denoted by sigma 2. If and only if the components, so let me say it differently, the matrix B is a symmetric matrix for any basis. And so in fact, it's symmetric if and only if the matrix is symmetric for some basis. And then once it's symmetric for one basis, it's symmetric for all bases. Okay. All right, and that just obviously comes from the definition. Okay. If B is symmetric, then BJK is equal to BKJ. All right. Okay, so good. Now, let's think about, so that's how you characterize symmetry. What about definiteness? So if I have a symmetric B, symmetric bilinear map, how can you tell if it's positive semi-definite, positive definite? Etc. All the other things as well, negative semi-definite or negative definite. How would you verify that, do you think? You've seen this probably when you talked about inner products and linear mappings on spaces with inner products. So let me ask you a question which is somehow related to this, but in a way that you have to be careful with, and that's kind of the point of talking about this. So if you have a linear map, so if you have a vector space V with an inner product, okay, and you have a linear map on V, all right, what does it mean for that linear map to be symmetric? Okay. So I have an inner product. Okay. And I have a linear map, A. Do you remember the definition for this thing to be symmetric? Have you seen that before or not?
Yes.
In 212, right? Okay. All right, so there's one of the things that's important here is that a symmetric linear map only makes sense on an inner product space. Okay, it doesn't make sense on a general vector space without any kind of an inner product. So the notion of a symmetric linear map is connected to inner products. Okay, so symmetric bilinear maps, on the other hand, definitely do not require inner products. It clearly makes sense to talk about a bilinear map being symmetric all by itself. Okay, but my question is this. And so if A is symmetric, what do you know about the eigenvalues of A if it's symmetric? What property do the eigenvalues possess? Correct, they are real. Okay. What else is true in terms of eigen stuff? Okay, so A has real eigenvalues. What else can you say about A in terms of its eigenvalues and eigenvectors?
You span the whole space.
That's right. So the space has a
Yeah.
basis of eigenvectors, and what else is true?
They are
You can find a
orthogonal.
basis. What additional property does it have?
They're orthogonal.
That's right. Okay. And V has, this is going to come back to visit us, and it'll have physical meaning later on in the course, but now is a good time to talk about it. Okay, so that's the aside. So this is kind of intended to recollect to you some things that you know about, which can maybe help us answer that question. Okay, because I have, so B is symmetric if its matrix is symmetric. Okay, now if I have a symmetric matrix, let's kind of just forget about the fact that we already know that a matrix representation of a bilinear map isn't really a linear map on the vector space itself, but let's sort of pretend like we don't know that and try to answer this question of when is a bilinear map going to be symmetric. So what I want to do is I want to come up with ways of answering this question in terms of the matrix of B. What do you think?
Is that the value of the eigenvalue?
Yeah, so what property should the eigenvalues have? Let's say if you're positive semi-definite.
Yeah, it's greater than equal or equal to 0.
Yeah, greater than or equal to 0, so non-negative. Okay, so answer. B is positive semi-definite if all eigenvalues of its matrix are greater than or equal to 0. Okay, and B is positive definite if all eigenvalues are greater than 0. Okay, all right, so now you are absolutely justified in saying, but you've written down some things that really don't make sense. Okay, and why am I pointing that out? Well, I'm talking about eigenvalues, right? But I'm talking about eigenvalues of not B, but the eigenvalues of the matrix of B. Okay, these are not eigenvalues of B. So normally, if you have a linear mapping on a vector space, the eigenvalues of the linear map are the same as the eigenvalues of the matrix. That's how you actually calculate the eigenvalues in practice, is you choose a basis, you write down a matrix associated to the linear map, and then you find the characteristic polynomial by taking determinants, right? In this case, I seem to be saying something that makes no sense. I'm talking about the eigenvalues of this matrix, but this matrix is representing a thing, B, which is not a linear map. So there's something fishy going on there. And there is something fishy going on there. And it's not that these statements are false, the statements are true. Okay, but you just have to be careful in understanding what they mean. So I'm just going to sort of say it out loud, what's going on here. So what's true is that if you take a bilinear mapping B, you write down its matrix representative, okay, and you calculate the eigenvalues of that matrix representative, then the eigenvalues are going to be positive if and only if, and so, okay, that is an if and only if and only if the eigenvalues of B are non-negative. Okay, so so the point is that this thing depends on the basis, okay? And if you change the basis, then this matrix is going to change, all right? The eigenvalues of the matrix are also going to change, okay? Because they're not eigenvalues of a linear map. It's not like B is a linear map, but the signs of the eigenvalues will not change, which is a very curious thing, okay? But it's true. To understand that requires a significant and rather confusing diversion that I'm just not going to take. All right, but that's a little thing for you to chew over if you are interested in this kind of stuff. Okay, so the point is that the signs of eigenvalues of matrices of bilinear maps don't change when you change the basis. Okay, so if 3 of them are positive, 4 of them are 0, and 10 of them are negative, then that statement is going to be true no matter what basis you choose to represent the bilinear map. Okay, all right, and so in practice, that's how you can check whether a bilinear mapping is positive, semi-definite, positive definite, negative semi-definite, negative definite, and so on. Okay. All right. Okay, so you'll be very happy to know, I imagine, that that's the end of our linear algebra diversion. All right. So now what we are going to do is we're going to go back to differential geometry. And then again, like I said, after we do that, we're going to go back to physics. Okay, and so what I'm going to do is I'm going to talk about all of this linear algebra stuff that we've been talking about, but in the context of a particular vector space that arises when we're talking about manifolds, and that's a tangent space. Okay, so if M is a manifold, if X is in M, and TXM is the tangent space, then the tangent space is a real vector space. Okay, and this is a homework problem. Okay, and so the idea in the homework problem is so you know that when you choose coordinates for the tangent bundle. Okay, so the coordinates for the tangent bundle look like x and v, and so these are vectors. So let me just make sure that we understand that these are vectors, not points in the manifold. So these are in, let's say, in coordinates, so they're in phi of u cross Rn. Okay, so this is what Tm looks like. Jack. In coordinates. Okay, so that's, we went through all this business of finding an atlas for the tangent bundle, and we, spent a lot of time talking about the fact that the natural atlas for the tangent bundle takes its values in, the subset of Rn cross Rn that looks like that. Okay, and so then you want to define addition and multiplication, scalar multiplication, in the tangent space in the obvious way in coordinates. Okay, and so if I take u and v in the tangent space, okay, so what that means is that in coordinates, these things look like t phi of u of u, so that's a small u. So let me just make sure that we understand that that's a small u, since coordinate charts have a big U lying around as well. Right, so that's a little u. Is going to look like phi of x, comma, let's say u bar, and the coordinate representation in the chart of v is going to be, it's again a tangent vector at x, so it's going to have the same point there, phi of x, comma, v bar. Okay, and you want to define u plus v in tx m. You want to define that by t phi of u plus v is equal to phi of x. So again, it's going to be a tangent vector at x, and so the points here, here, and here are the same because it's a tangent vector at the same point. And the way you want to define that is that it's u bar plus v bar. Okay, so you do the normal vector addition in coordinates. Okay, and similarly, if A is in R, then T phi of A V, let's say, is V of phi of X, A V bar. Okay, so that's how you define you define addition and scalar multiplication by doing it in coordinates. Okay, and now, but you have to show actually, so you must show that these definitions are independent of coordinate chart. Okay, and that's what the homework problem is. Okay, so I'm going to take the homework problem for granted. So we know that I can define addition and scalar multiplication on the tangent space by doing it in coordinates like this. Okay. All right. So the point is, the upshot of that little discussion is that this is a vector space. Okay, and if you like examples of vector spaces that are not Rn, okay, this is an example of a vector space that is not Rn, right? In fact, this is a sort of a complicated construction, right? Remember how we defined a tangent vector. We defined a tangent vector, piece of equipment out my window. I defined a tangent vector to be an equivalence class of curves, and the tangent space is the set of all equivalence classes of curves, and that's not Rn, right? So this is a bona fide example of an abstract vector space, but nonetheless, it's a vector space. The dimension, so if M is n dimensional, then so is the tangent space. Okay, now we had this first quiz where we show that we have examples of manifolds that don't have a well-defined dimension. But what we saw in that example is that a manifold that doesn't have a well-defined dimension is kind of disjoint components, each of which has a well-defined dimension. And so every point in M is going to be in some component of M that has a well-defined dimension. And so, therefore, this statement gives you the dimension of the tangent space, which is that it's the dimension of the component of M that contains the point X. Okay. All right. So what we're going to do is we're going to find a basis for the tangent space given a chart. U phi for M. Okay. All right, so then once we have a basis for M, then we're kind of in the situation that we talked about when we were talking about linear algebra, right? So you can talk about dual spaces and dual bases. You can talk about bilinear maps and bases for bilinear maps. You can talk about the change of coordinate rule, all that stuff that we talked about for linear algebra. We're going to do that, but we're going to do it for tangent spaces. And the main upshot of all of this is just like really our discussion of linear algebra introduced really no new linear algebraic concepts. It introduced notation for talking about algebraic things that you already know about. The same is going to be true here. The main idea is going to be to introduce some notation that's very useful notation to work with and for representing things. So it's not just notation, it's very useful notation, but it's notation. Okay, so it doesn't change the concepts of tangent vector and tangent space. It just gives us a representation of those things and a notation for representing them. Okay, all right, so enough of the sort of build up. So what's the picture here? So first, maybe let me give the definition. So let M be a manifold and let U phi be a chart for M. Okay, and I'm going to take a point X in U. Okay, now what I will do is I'm going to define a tangent vector, and this tangent vector is going to have what is going to look right now to be extremely silly notation for it, but we'll see that this notation has good cause. So, but for now, I agree, it's just going to look silly. Okay, so you use this kind of funny partial derivative notation, okay, for a tangent vector, and the tangent vector is going to be at X, right? Okay, so here's how you define that tangent vector. Okay, so the chart U phi induces, as we've seen, a chart TU T phi for TM, okay? And I'm going to require that T phi of this tangent vector to be equal to phi of x, comma, EJ. Okay, and this is none other than, so it's in Rn, because when we take T phi maps us into Rn cross Rn. The second part here is the vector part, right? And the vector part of this tangent vector is the jth standard basis vector, right? So this is the jth that we've seen before. Okay. All right, so then okay, so then we have a basis for the tangent space, which has this funny notation, and a lot of what we're going to do is going to be just sort of teaching you how to do manipulations with this notation. Okay, so I don't really have much more time today to talk about much, but what we're going to do next time is we're going to look sort of at this notation in more detail, see how to use it. We're going to talk about something which you're sort of familiar with from vector calculus, the idea of a vector field. So we're going to talk about vector fields and changes of coordinates, inducing changes of basis. Okay, so that's how we're going to be occupying ourselves for the next little while. Okay.